In this video, we'll talk through the 2023 National 5 Chemistry paper and explain how I would approach each question. Starting off with the multiple choice. Question 1 asks us to use the average rate calculation. We will find that in a data booklet. Average rate equals the change in quantity over the change in time. In this question, they do not want us to calculate the average rate. They want us to calculate the total volume of gas that's being produced. Two ways of knowing that. Well, one at the top, it tells us the average rate is 5 centimeters cubed per second. Also tells us the time is 60 seconds. What I would do, I would rearrange this relationship. Therefore, my change in the volume will be the rate times the change in time. Plugging in my numbers, that's going to equal 5 times 60 equals 300 centimeters cubed. Gives us an answer of E. More typically, you'd be asked to just calculate the rate. This one's, I've changed it around. Our answer is D. Next, question number 2, we're asked about a proton. Protons are positively charged. That rules out B and C. They are found in the nucleus. That leaves in A and D. They have a mass of 1. A would be our correct answer. If you're looking at an electron, electron is going to be negatively charged and found outside of the nucleus. If you were asked about a neutron, it has no charge, found in the nucleus. That's not actually an option in this one. So a nucleus would have a mass of 1, a charge of 0, but it would be found inside the nucleus. So that doesn't match up. Question 3, we need to know about the shapes of molecules. 4 shapes you need to be aware of are linear, angular, trigonal pyramidal, and tetrahedral. Chemical A has a carbon with 4 fluorines around it. That would likely be tetrahedral. Next one, we have one thing in the middle with 3 around it, likely to be trigonal pyramidal. Next one, we have SCl2, which is likely to be angular, and then D is likely to be linear. So our answer would C. If you're not given the formulas, but you're given the names, work out what the formula of that chemical is, and then match it to the correct shape. Number 4, we're looking at lithium fluoride. Lithium fluoride, we have a metal and we have a non-metal. You can use the data booklet to classify them. We have lithium, we have fluorine. Lithium is on the left of the dark line, so it's a metal. Fluorine's on the right side, so it's a non-metal. Something else that can help us is if we look down on page number 9, they have got lists of ionic and covalent compounds. We can see what lithium bromide is classed as being ionic. And if we go up, bromine is also a non-metal. This means that lithium fluoride is likely to be an ionic substance. If there was any information about properties such as conducting electricity, melting points and boiling points, that's more important than just is it metal and non-metal. In this question, it's all we've got to play with. We need to then know about the 4 different types of bonding and structure that can be represented. If there are delocalized electrons, that is metallic lattice. Not what we want in this question. Next one, we have positive and negative ions. That is an ionic lattice. That will be our answer for this question. Next up, we would have covalent molecular. And not the answer to this question. And the bottom shape is going to be our covalent network. Depending on the chemicals, you might have to pick a different option. Number 5. In which of the following compounds does the iron have a 3+ charge? Right, let's go through these then. We have got iron and we have got oxygen. If we find oxygen in the data booklet, for oxygen to become stable, it will have to gain 2 electrons. You gain 2 electrons, it's going to become negatively charged. It's going to have a 2 negative charge. So when we go back out to here, this is 2 negative, and there is no charge overall. Your iron must have a 2 positive charge. Now those balance out, which is why we just write it as FeO. That, therefore, is not going to be our correct answer. Similarly for phosphorus, which is here. Well, phosphorus will need to gain 3 electrons. If it gains 3 electrons, it's then going to become E3 negative. As a result, if it's going to be the negative, the ion that is joined to it is going to need to be 3 positive, and then that is just written as Fe. And that will mean that is going to be our correct answer. Going through the other ones, here we have groups. This is nitrate and phosphate. If you don't recognise it, you can look down on page 8. We have those things here. Going for the nitrate first. Nitrate tells us that it's got a 1 negative charge. Key is, for this one, that we have got 2 nitrates. This means this would have a 2 negative charge overall, because it's 1 from each of them. If that's the case, your ion has to be 2 positive. Therefore, that is what gives us the FeNO3. That's not going to be our answer in this question. In the last one, we have got phosphate. Phosphate is over here with a 3 negative charge. You have got 2 things that each are 3 negative. Overall, that will give you a 6 negative charge. We have got, this time, 3 ions. We need to balance out that 6 negative using 3 ions. 3 ions, each with a 2 positive charge, will balance out the charge. And that's not going to be our answer. We want the one that's 3 plus, which is B for number 5. Next, we want the least number of moles of solute. This means we're using one of the calculations involving N for number of moles. You need to be able to recognise that is a volume and that is a concentration. That means we are using N equals C times V. When you're using this, because it is moles per litre, we want our volumes in litres. So if you have something in centimetres cubed, if you divide by 1,000, you will turn that into litres. Concentration for the first one is 1. 100 divided by 1,000 is 0.1. You can use your calculator to tell you that. And then 1 times 0.1 is still 0.1 moles. On to the next one. N equals CV. 0.75 times 150 divided by 1,000 will give you 0.15. Multiply them together. Not doing that in my head. It comes out as 0.1125 moles. Next up, that's going to be 0.6 times 200 divided by 1,000 is 0.2. Gives 0.12 moles. And lastly, that's going to be 0.25 times 0.25. 250 divided by 1,000 is 0.25. That comes out as 0.0625. Answer would be D. Moving to the next one. Next one, which of the following substances, when shaken with water, would cause the pH of water to increase? If the pH goes up, that's going to make us have a basic or alkaline solution. If you have a soluble metal oxide, they are the ones that form alkalis. If you have soluble non-metal oxides, they will form acids. You can use the data booklet again. I would first rule out any non-metals because they would form an acid if they dissolved. Aluminium, barium, nitrogen, and hydrogen. Aluminium, barium, nitrogen, and hydrogen. Aluminium, barium are metals. Hydrogen and nitrogen are non-metals. The hydrogen one's not too clear on this page because the dark line has gone away. I go up to page number 4. That's got it a lot more clearly that it is above the thick dark line there. And the ones that are below it are metals, so hydrogen is a non-metal. This means we're down to just 2. Second important part is it has to be soluble in order to change the pH of water. We can check solubility on page on page 8. Use this table. Well, we run it along for the barium, down for the oxide. Where they overlap is the chemical we're looking for. Next chemical was aluminium. Run that across, run that down. We're looking at this chemical. The aluminium one is insoluble. It does not dissolve. Therefore, it would not change the pH. Barium one is soluble. It would change the pH. It is going to be our answer for that question. Next up, here we're talking about reactions of acids with different chemicals. One reaction we need to know about is acid plus base makes salt plus water. 3 main types of bases. Those would be hydroxides, oxides, and carbonates. What I'm noticing here is that 2 of the chemicals are bases. And we've just got a metal for the nickel one at the end. What happens with that is, if we have a metal plus acid, we would still make the salt, but we're going to make hydrogen instead of water. If the question wanted carbonates, carbon dioxide would also be produced, but that won't matter too much, I don't think, or maybe it will. Let's have a look. Which of the following is true for all 3 reactions? A gas is produced. Well, if we use the carbonate, we would make carbon dioxide. So for that one, so if we're talking about for gas being produced, yes for the carbonate, carbon dioxide. No for the hydroxide, but yes for the nickel, because that would make the hydrogen. Doesn't happen for all 3, so let's rule that out. Water would be produced for the bases, but if you just use a metal, you make hydrogen, not water, so that's ruled out. Your salt is produced every time. The name of the salt would come from the metal in the starting material, so nickel in all of them. Sulfuric acid produces sulfate salts, so that's going to be true. A neutralization reaction happens when you have an acid and a base. One of the experiments, that last one, is using a metal. A metal is not a base, so we would not have a neutralization reaction technically for that one. They are sometimes thought about as neutralization because it gets rid of the acid, but a neutralization has to make water, and that doesn't happen in that one. Here we're looking for spectator ions. Spectator ions remain unchanged. Yeah. First of all, if we look at the sodium, we have sodium ions in solution at the start. We have sodium ions in solution at the end. This means it's a spectator ion, so we will remove that from the equation when we do our final equation. We then have carbonate ions. On the far side, it's changed, it's lost an oxygen, it's become carbon dioxide. That means it has to be included in our final equation. It is not a spectator ion. The hydrogen ions are in solution. They have joined onto the oxygen and become our water. The hydrogen ions have changed and converted into water by adding on an oxygen. This means we need to keep it in our equation. It is not a spectator ion. The chlorine is in solution, and at the end it's still in solution, meaning it is a spectator ion. We can ignore it from our final equation. C has sodium ions. Those are the spectator ions, so we can get rid of them. We're looking at what we've got left over, so I need a CO32 negative. That one doesn't have it. We need 2 hydrogen ions. Oh, if we actually look here, it's CO32 negative aqueous. This one says it's got a gas, so C is getting ruled out by me for that reason. B is going to be the correct answer. We've got our 2 hydrogen ions. We have our carbonate ion. We have our water as a liquid, and we have our carbon dioxide as a gas. B would be the correct answer. A lot of questions would ask you to identify the spectator ions, in which case is the ones that are highlighted in red those are the spectator ions. A bit of a quicker way to do that, if you're looking for a spectator ion, if we have aqueous solutions at the beginning, if it remains in solution, it's not changed. So the sodium and chloride are going to be our spectator ions. So we want to remove them from our equation to get our final answer for that. Two ways of doing the same thing, but B would be correct for that one. Next up, we're asked to name this chemical. I would sketch it out just to make life a little bit easier. So we have a carbon with 3 hydrogens. We have carbon with a methyl group, that's what that's called, CH3, and a H. So that bit there is that bit there. Next up, we have a carbon with 2 hydrogens. If it's got 2 hydrogens on it, it has to be part of the chain. Then on to this carbon. It says that we've got 2 CH3s on it, like so. And then we've got our CH3 at end. This, to me, will be easier to name rather than looking at the shortened formula. First thing to do, what is the longest chain of carbons? Straight through the middle. 5 carbons would give us the beginning of pent. It has single bonds between the carbons. It's going to be pentane. Page 9 has a list of the different chemicals we can find out. And look there to make sure, if you ever forget how many carbons is for pent or hex or whatever it might be. This rules out the pentenes. Pentenes would be if we needed double bonds to fill up the correct number of bonds. Next, we have got 3 methyl groups. That's why they all have trimethyl. But it's either going to be 2,2,4 or 2,4,4. It depends on which way we number, and there is a correct way of numbering. If you were to number, going from left to right, well, we would have 1 methyl group off of the second carbon and 2 off the 4. So that would make 2,4,4 correct. However, if we correctly go to make the numbers the smallest we possibly can and go from right to left, you have got 2 methyl groups on the second and just 1 on the fourth. That would give you 2,2,4 trimethyl pentane. I'd say it's always easier if you sketch out the chemical so you can see how it's all arranged, and that would get us answer A. Next up, we're looking for an isomer of methyl butane. If we count up the numbers of carbons and hydrogens first, we have got 5 carbons and we have got 10 hydrogens. I would just check, do we have the same in these ones? We have got C5H10. We have got C5H12 for B, ruled out instantly. We have got C5H10. And we have got C6H12. With this one, both of A and C have the same number of carbons and hydrogens. Now, the kind of trick here, they do look different. However, if I was to describe what I see, I've got 4 carbons connected together. And I've got carbon to carbon double bond in the middle, so between the second and the third. Also then got a CH3 group, a methyl group, off of the second carbon. If I look here, I've got 4 carbons in a row. I've got a carbon to carbon double bond between the second and the third. If we take the number to get the smallest value, this would also be off of the second. These two are not isomers, they are exactly the same chemical. A is also 2-methyl-butane. Whereas, if we go down to C, C is cyclopentane. It has got a different name, it's arranged differently, it is an isomer, so C is the correct answer. Number 12. Which of the following would not be produced by an addition reaction of butane? So starting off, what does butane look like? It's 4 carbons, eth prop but. Double bond is going to go in there. Fill up, so every carbon is making 4 bonds. In an addition reaction, we're going to break the double bond between the carbons, and we're going to put some other chemicals added to those points. Now, if I look at what we have here, we've got a CH3, CH3, and they're saying here we've got CH2 and CH2. Well, if we added hydrogen, that would work out as our answer. We can go between those two by adding hydrogen and breaking the carbon-to-carbon double bond. I'm going to say that one's correct. It's not our answer, because it's saying which one's not. Next up, well, what we are trying to do is we again want to put in our two H's. They're also wanting an OH group on the end. That's not how an addition reaction works. Addition reaction only adds to where the double bond was. Double bond is between 2 and 3, and that's where we add the atoms. So that is not a possibility. And the wording of the question, that is our answer for number 12. Check the other ones. We have got a CH. They're wanting an OH here. Then the next carbon, they want a hydrogen. If you added water, that would achieve that. So an addition reaction involving water is called a hydration. It forms an alcohol. That is a possibility. So we could make that so it's not our answer. Lastly, we have now got bromines in there. So if you decolorize bromine water in an addition reaction, you would be able to make that. Therefore, it's not our answer. So we're checking where are they adding these new atoms. It needs to be added in this region. If it's not going to be our correct answer. Next up, they are talking about chemicals called ketones. Ketones are not part of the National 5 chemistry course, but it is part of the higher course. And these ones, they are telling us that these chemicals exist. All the information we need should be here to answer the question. What am I looking for? What are we changing as we go from left to right? I'm going to first look at the bits that stay exactly the same. That is as it is. That is exactly as it is. We are going to need to lose this OH group. We're also going to lose this OH, that carbon, and that oxygen. And then we're left with those ones. The bits in red, well, where are they going? Well, if you look there, we've got 1 carbon and 2 oxygens. That would be those parts there. Give you CO2. And then you've also got H2O. So they parts are used to make the carbon dioxide and the water. We are going to repeat what's happened with the chemical underneath it. What do I mean by that? That's going to stay. That's going to stay. The hydroxyl group off of the first one. That hydroxyl group is going to go. And then our carbon double bond oxygen is going to be removed as well. And then all we need to do is pop them together. If we look at the first one, that actually works out perfectly. Got our H5C2, C double bond O, E5H11. That will be our correct answer. Next one, what's the issue? Well, we've got a C2H5, but it's supposed to be that. So what they've done there is they've used chemical from before to try and trick us. I'm not going to let that happen in this question anyway. Next up, problem. We've got C11H5. Just not what we've got on that side. Oh, so they've got the same groups on each side, so that's wrong. Lastly, they've used a methyl group. Not what we've got. We've got C2H5. Again, that's wrong. So it's following the pattern, looking at what changes, what stays the same, and that will hopefully help you get the answer. We're talking about methanol versus octanol. That's 1 carbon. That's 8 carbons. We want methanol. Describe methanol compared to octanol. Methanol is smaller. If it's smaller, it will have a lower formula mass. If it's smaller, it will dissolve more easily. Answer would be D. If we try to dissolve a sugar cube versus ground up sugar, the smaller particles will dissolve more easily. Same idea with methanol and octanol. Next to them, which of the following is correct for both of the molecules below? They can be represented by CnH2n. N means number. We've got 4 carbons. H, 2N means it's twice as many. So 2 times 4 would give you 8. This one is C4H10. This one is C4H8. That is not correct for both of them. They have the same melting point. Okay, ask us about the same melting point. We need to know what these are called. This is butane. The other one is cyclobutane. Okay, same melting point. Different numbers. Not going to be our correct answer. Answer C is incorrect. Hydrocarbons don't dissolve in water. Try to think of the best way of explaining this. There is terms from like sort of higher chemistry that help explain it. Best way I can think of explaining this, they come from crude oil. They are compounds taken from crude oil when it's been fractionally distilled and separated out. And oily things don't dissolve in water. If you've ever had oil and water together, you'd have noticed that. It's just not the answer. I know that's not a very satisfying explanation, but it's just not right. If we look at the next one, saturated means that there's single bonds between the carbons, and that both of them do satisfy that. So I'm kind of going off the fact that that's definitely correct. My explanation for why C is wrong is terrible. If you've got any ideas of a better way of explaining it, please share them with me. But D would be the correct answer anyway for that one. Sodium methanoate could be produced by different reactions. We have got here sodium oxide is a metal oxide, so it's a base. And it's a base and alcohol. We've then got sodium chloride, which is an example of a salt, and an acid. We've got a base and acid for C. And then we have a metal and an alcohol. Sodium methanoate would be an example of a salt formed when a carboxylic acid reacts with a base. So it's quite well, it's the same reason as acid plus base makes salt plus water. So for example, if it was hydrochloric acid and sodium hydroxide, you would make sodium chloride and water. When you have something like methanoic acid plus, again, it's sodium hydroxide, you would make sodium methanoate. You'd make ethanoate, propanoate, just depends on what chemicals we're using. So the fact that that's what's been made, we want a base and an acid. We want the correct base and acid. So those two together would make sodium methanoate and water. So 16 would be C. On to 17, properties of a metal. The sentences to remember: metals always conduct. Now, instantaneously is the right answer. If you're asked about the other ones, ionic, sometimes. And that would lead us to C being the right answer. Covalent never conducts unless it's carbon graphite. It's usually never carbon graphite. That leads us to B and D being our covalent chemicals. Networks have higher melting points and boiling points. MP and EP. So of the two, the bottom one would be our network, and this one would be covalent molecular. If you remember those, that will get that every single time. Here we're talking about reaction of metals in increasing reactivity. So this is from low to high. Look what we've got. Well, Z reacts with everything. That would be my most reactive element. X and Y both don't react with water, but it does. X reacts with oxygen and phthalic acid. I'm going to put that as my middle reactivity. And why is the least reactive? Because it reacts with the least amount of stuff. That's oversimplifying it, but that would give me B as the correct answer. Onwards, we're talking about flow of electricity in an electrochemical cell. It flows from high to low in the electrochemical series. So we just need to look at nickel, zinc, aluminium, and see which one has A. Metal A is higher than metal B. So nickel and zinc first of all. So it would flow from zinc to nickel. That is not what's happening in that one. Next, it's zinc and aluminium. It would go from aluminium to zinc. So that would again be the wrong way. So both of those have metal B is more reactive than metal A. Aluminium and magnesium. Again, it's not going to work. It would go magnesium to aluminium. Then last up, we've got aluminium to nickel, which will be the correct answer. Electrons would move from aluminium down to the nickel. E for 19. Next up, number 20. We're looking to combine an oxidation and a reduction equation. At the moment, electrons are on the same side for both of them. We need one to be an oxidation and one to be a reduction. It's magnesium and it's silver. Same logic as before. We're going to go from the one that's higher up to the one that's lower down. So magnesium is going to lose electrons. It's going to be oxidized. Silver will gain electrons. It will be reduced. Something that can help with this topic would be oil rig. Oxidation is loss, reduction is gain. What this means is the silver equation we can leave as it is, because all of these equations on page 10 are the reductions. But magnesium, we will need to flip round. We need to reverse that equation. What I would do to make our life easier is I'm going to take the MgS, which was on the right, now on the left, have our arrow, and we've got our Mg2 plus 2 electrons. And now that one, we're not needing anymore. So this is oxidation, this is reduction. Next up, before you combine them, they have to have the same number of electrons. This means this bottom one needs to be multiplied by 2. Let's put a 2 in front of all of those. If we can imagine that we split this down the middle, we've got everything on the left together, everything on the right together, we can cancel out these electrons. That's why we needed both of them to have the same. D and D both contain electrons. In a redox equation, there are no electrons present, so let's get rid of that. We now just need to follow along with what we've been shown at the top. So we've got magnesium solid on the left, silver ions on the left as well. A matches that. If you look at this one here, they have not flipped that equation. And that would rule out that, given as A is the answer for that one. In this case, we have to remember the reactants and products for the two different reactions, the Haber and the Oswald. So Haber uses nitrogen and hydrogen to form ammonia. So Haber is not got ammonia as a reactant. Let's roll that one out. Haber does use nitrogen to make ammonia. So that one's going to be correct. If the question wanted about Oswald, Oswald uses ammonia and water and oxygen, but to form nitric acid. And they're saying here that yes, Oswald uses ammonia, but it doesn't make nitrogen. Oswald makes nitric acid from ammonia. So those two would be the other way around if that was the correct answer for that. NH3 is ammonia. That's your nitrogen and hydrogen there. Next up, we're talking about different decays of radioactive isotopes. You have got alpha particles, which are 4-2He. There is beta, is 0, -1, and E. Now, we are looking at alpha particles. We are starting off with a mass of 227. If that then loses an alpha particle, it will lose 4 from its mass number. So from 227, it would go to 223. We're not quite there yet. So we could repeat that and keep going until we get to the final value that we've got. Like so. We have in total lost 1, 2, 3, 4 alpha particles. That would give us the correct answer of 4. So C, number 22. I've just put question marks. I've not bothered to look up which elements they are because it makes no difference to this question. You would just use the atomic numbers in the periodic table and look them up, and then you'd find out what they are, but it doesn't matter for the purposes of this. Another thing you could do, which would speed this up considerably, well, if you start at 227 and you go to 211, we have lost 16 of a mass. Each alpha particle is 4, so we would need 4 alpha particles, because 4 times 4 gives you 16. Either of those ways works. Getting up to 4, it's not too taxing to write it out like that. If there was more and more, then that would, the other approach would kind of have to be used, I'd say, for time purposes. Next up, which salt cannot be produced by a precipitation reaction? So in a precipitation reaction, solid formed from solutions. I reckon if we look that up, same way as before, on page number 8, only one of these should be soluble. That will be our answer for this one. So barium sulfate, lead sulfate, calcium chloride, and sodium chloride. Only the calcium chloride is soluble, gives us an answer of C. So we need to know that if you make a precipitate, it's a solid. So we'll use that page and it'll tell you there. In this question, they're talking about Benedict's and iodine tests. These are now more typically done in biology, talking about photosynthesis and plants making starch and all that good stuff. So we're talking about flame testing, give the colour changes, and we're also talking about the results for glucose and starch. Okay, which mixture could produce this? So, either glucose or starch. The results they say is that Benedict's turns from blue to orange, and this means that there would be glucose present. No starch, because starch would have gone blue-black with iodine. So starch and iodine would give you blue-black. Right, so there's no starch. My first thought. Let's get those away. So starchy ones away. Next, we're talking about sodium versus strontium, and this is to do with the flame colour. Now, if it happens that your favourite element is strontium because it burns with a red flame, you can rule that one out. If you're not as fortunate as that, you can get them on page 6. And on page 6, we'll see that strontium is red, sodium is yellow. Therefore, it would have to be the sodium, chloride, and glucose give those particular results. So even if you're not familiar with Benedict's or iodine, it tells you the results there, and you just need to pick the right options. Next up, last question on multiple choice. In this question, we're asked to work out the number of moles of sodium hydroxide required to neutralise the acid. First thing I would identify is which two chemicals are we talking about? Well, it's sodium hydroxide and it's sodium hydroxide. It's sulfuric acid and it's sodium hydroxide. They tell us that the number of moles is 0.002 moles. More typically, you'd need to work that out using NCV, but we don't need to, so that's nice. We then need to look at our ratio of sulfuric acid to sodium hydroxide. We have got 1 sulfuric acid to 2 sodium hydroxides. This means we need to take our number of moles and we need to multiply it by 2, 0.004. Now we know the number of moles is 0.004. The question wants the number of moles, so that would just be our answer. I would, I think a lot of people would try and use this concentration here. We don't need to, because the question starts us off with number of moles and asks you for number of moles. So you need to make sure you know what you're started with, and don't just go on like autopilot and go, I need to use NCV, ratio, NCV. In this question, they've kind of flipped it a little bit. They've changed that a bit, so we don't need to do those. We have to state the number of elements, including chlorine, that exist as diatomic elements. My way of remembering it is hin, bockle, brr. We've got 1, 2, 3, 4, 5, 6, and 7. Another way people remember it would be going in a 7 shape from 7. 7's quite helpful. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, but also hydrogen, and there are 7 elements there. Moving on. Next, we have been told there are 2 different isotopes of chlorine, 35 and 37, and we've told what the average is. We are looking, our average is closest to 35. That will be the most common isotope. The one that's closest to the average is the most common. If the average sat exactly halfway between, that would mean you have a 50-50 split. So neither of them would be more common. They'd be exactly the same proportions. Next up, name an element that has a similar chemical property to chlorine. This means it's in the same group. It will also have 7 outer electrons. So anything from fluorine, bromine, iodine down to astatine. I'd probably just go fluorine because it's the first one there. So fluorine. Next up, we have got our Euclid notation. And this is this funky looking thing. We have got our mass on top, and we have got our atomic number on the bottom. So, starting from scratch, if you have an atomic number of 12, atomic number tells you the number of protons. So, for the first one, protons equals 12. If it was an atom, so uncharged, it would have 12 electrons. However, we are sitting at 2 positive. This means that we must have lost 2 electrons. Electrons are negatively charged. We have only got 10 electrons now. If you are confused by that, if you don't get what I'm on about, well, look here. We have got magnesium here. How would magnesium become stable like something in the noble gases? It would lose its 2 outer electrons. It would become 2 positive. Down here as well, these are all metals, and the metals have all become positively charged. If they were in group 2, like barium, same as magnesium and calcium and strontium, they're all 2+, because they've got 2 outer electrons to lose. Any way you look at it, 10 is the right answer for that one. For the number of neutrons, which we don't need for magnesium, but I'll do it anyway. You take away the 2 numbers, so mass take away atomic number gives you the number of neutrons. On to the chlorine one. Again, we don't need the protons, I've told this, but protons would equal 17 because of the atomic number, the bottom number in that notation. Electrons, if it was an atom, would also equal 17. We, however, are negatively charged, which means we have gained 1 electron, which gives you 18. If you go back to here, chlorine is 287. To become stable, it would add on a negative electron, and it would become negatively charged, and that would work out for that. And then to get the neutrons, you take away the protons away from the mass number. So 37 take away 17 gives you 20. And that is that question done. Number 2, use the terms to describe compounds that only contain hydrogen and carbon atoms. Hydrogen, those are hydrocarbons. Next up, state the name of the chemical X produced in this reaction. Those have still stayed the same. Those have disappeared. That gives you hydrogen. That would answer. Got. Next, show that something is unsaturated. This means it contains carbon to carbon double bonds. Saturated single bonds between carbons. Unsaturated, got carbon to carbon double bonds. We would use bromine, solution, or water. Would be decolorized by unsaturated compounds. And that would be something like your ethene. Next up, ethene contains a triple bond between carbons. Draw the structure formula of ethene. Eth is 2 carbons. You can see that if we go down. So meth would be 1 and eth would be 2. So I'm going to do that first. 1, 2. It's got a triple bond. Carbon is in group 4, so it's going to make 4 bonds. It's currently making 3. So we would put on a hydrogen in each of them. When it says full structure, you need to draw out all the bonds. So you would not be allowed, you would not pick up the mark if you just wrote it like that. We want to show all the bonds. Next up, we are talking about burning a hydrocarbon and plentiful supply of oxygen. This is what's known as complete combustion. If you're burning a hydrocarbon, you would make carbon dioxide plus water. Next, we're talking about exothermic. Exothermic means energy is released to the surroundings. If it was endothermic, energy is taken in from the surroundings, so it's absorbed from the surroundings. Okay, the columns in the periodic table are known as groups. State a group number in which all the elements are metals. A bit of help that the metals are on the left-hand side of the periodic table. Group 1 is out because of hydrogen. Group 2 looks good. Group 3 is out, and then all the rest of them are out. It's only group 2 has all of them. Hydrogen is not a metal. If you went to page 6, you might get confused because it's not clear. Like, this should really cut across and show you that hydrogen's a non-metal. So page 4 is going to be more helpful in that one. So yeah, group 2. Next up, we have to write a formula for potassium permanganate. Potassium is an element, has the symbol of K. We need to find out the valency, so how many bonds will it make. We can do that down on one of the periodic table pages. Anything in group number 1 will make 1 bond. Potassium needs to lose 1 electron. It's going to be a valency of 1. If it ends in 8, go to page 8. Formula should be there. We have our permanganate. For these questions, it's MnO4. Unless it asks you for what's called the ionic formula, we don't need to show the negative sign. But it's helpful because it tells us that it makes 1 bond. So what I would then do is write in my MnO4. Also makes 1 bond. We swap them over. The formula would just be KMnO4. You would not be credited if you had KMnO4 negative. If you put the charge in for both of them, so K plus MnO4 negative, that is okay. I would stick with just KMnO4. In this question, we're told observations of reactions of different metals, and we have to suggest a name based on these reactions. If there's just a dull glow, that will be least reactive of the 4 down to most reactive. This means it will be less reactive than magnesium, but more reactive than iron. Magnesium, iron. So zinc or aluminium would work out for those. For aluminium as my answer. Next up, we have to look at our gas test. There are 3 gas tests you need to know. Oxygen relights a glowing splint. Hydrogen burns with a squeaky pop. and carbon dioxide turns lime water cloudy. Now, we've got metals reacting with hydrochloric acid. So if we had metal hydrochloric acid, is HCl. The metal comes in, it kicks out the hydrogen. We would get our metal chloride plus our hydrogen. So that could be sodium, whatever it may be. So our answer is to do with the hydrogen. There's two parts that you need to know which of the three, then also how you test for it. So it burns squeaky pop. Could just say pop, I can't. Again, next up we have got to look at our voltages. So we are comparing chemicals. So in a cell, the further apart the metals on the electrochemical series, higher the voltage. So they're combined to copper, and it's magnesium, tin, and iron. So we are asked about iron. Iron is midway between the two of them. So we're looking for any number that's bigger than 0.5 but lower than 2.7. What's going to be halfway sort of between them? Or something along that sort of region. Yeah, so just further apart, the bigger the voltage, and then that gets you that there. What is meant by the term electrolyte? You have an ionic solution that conducts electricity. Yeah, so something like sodium, like salt, sodium chloride, or you can use a few different other ones, but that would allow the circuit to run, completes the circuit, something like that. Suggest one factor that should be kept constant to make this experiment fair. So we are changing the type of metal, so that's been changed. Everything else, all the other parts of it need to be kept the same. So volume, concentration, and type of solution. We only need one of these. So type or concentration. Your size of the electrodes, that's those metal pieces that you're putting in, they should be kept same or as similar as you can. Temperature can have an effect on how a battery or cell runs. What else have we got? Things like how far into the solution the metals are held, again, could make a difference. So that might be something. So any of those ones, I'd probably go for the volume or type or concentration of solution. Just need one of them, fix the mark. Next up, we need to read this passage and answer the questions. State where the carbon dioxide for industrial scale method extracted from the air is there. Just as simply as that. One advantage of using a catalyst is that they speed up chemical reactions. Doesn't tell you in here, so this is just from your knowledge. Catalyst speeds up chemical reaction. It is not used up in the reaction. It remains unchanged, whichever way you want to word it. Calculate the number of moles of carbon dioxide required to produce 5 litres of jet fuel using the new catalyst for that. So we are dealing with this bottom sentence here. So 4,700 grams would make 1 litre. A few ways of doing this. The way I like to do it, well, if 4,700 grams would give you 1 litre, then to get 5 litres, that's 5 times bigger. So we would need 5 times as much carbon dioxide. So 5 times 4,700 grams. This will give us 23,500 grams. Question wants the number of moles. Data booklet states that N equals M over GFM, so mass divided by the GFM. Maybe our 23,500 divided by carbon dioxide is CO2. Di means 2, carbon and oxygen. We can work out the GFM by dragging down our values. We have 1 carbon, we have 2 oxygens. Those are quite fairly common chemicals to use in these questions. You might know that carbon is 12, if not, there it's there. Oxygen is 16. Then don't remember, that's fine. It's here, tells you it's 16. So 1 times 12, 2 times 16, 32 and 12 gives you 44. Again, use your calculator to double check or to get your answer. Plug in the numbers, spits out a number of moles of 534. How far will I round it? Let's go 0.1 moles of carbon dioxide. So it's finding out what you've got, scaling it up, and then working out your number of moles like that. Question number 5 is the first of our using our knowledge of chemistry questions, asking us about the chemistry of nitrogen. Nitrogen is a non-metal element. It's one of our diatomic elements. This as N2, that's what diatomic means. It's got a triple bond between its atoms. If you don't know that off the top of your head, it has a valency of 3 because it's in group 2. It needs to bind to itself because it's a diatomic element, and it's going to have a triple bond between those. So it's covalent molecular is the bonding and structure. That means it does not conduct electricity. Covalent molecules have low melting points and boiling points. That means it's going to be a gas at room temperature. Could choose to speak about the Haber process at this point as well. So ammonia is formed during the Haber process. Hydrogen and nitrogen combine to form the ammonia. Balanced equation in there. There's an iron catalyst that's used. Oswald process turns the ammonia into nitric acid. Nitric acid is HNO3. Nitric acid is used to make fertilizers. So nitrogen, potassium, and phosphorus are important nutrients for plants. I can't think of any other piece of information we could put at the moment. There might well be. All we have to do is give a good answer to get all 3 marks. A reasonable answer would get you 2, and a limited answer would get you 1. So hopefully this would be enough to pick up the whole 3 points. Next up, question 6. We need to know our functional groups. This one is in a carboxylic acid. It is the carboxyl functional group. Other one you need to be aware of is the one that's present in alcohols, which is just the O and the H. And that is called the hydroxyl group. So hydroxyl, in this case, it's carboxyl. The type of reaction that takes place when monomers join to form polymers. For us, there's only one reaction that happens. It's where the double bond breaks, opens out, and we can add other monomers to each side. It is an addition polymerization. To draw a section of polypropenoic acid, and we're showing 3 of them joining together. So what we need to do is we need to take our monomer, we're going to break the carbon-to-carbon double bond. The parts at the top and the bottom will remain exactly the same, but we have freed up space on either side. That is what's called the repeating unit. This means we're going to have 6 carbons through the middle. Make sure you have lines on either side. The top had C, then COOH. Trying to make sure I space it out a bit better this time. H goes there. Carbon, OOH. And on the bottom was just hydrogens. So all of my bonds at the bottom go to H's. And that would be my answer. Putting square brackets on the end is showing that it's a section of the chain, but we need to make sure that the bonds are going to the right places, and we need those bonds on the ends as well. Next up, we have got polymers that absorb water and swell. It's affected by the salts dissolved in the water. Okay, Using the graph, identify the combination of material and salt solution that results in the most swelling. So the highest peak would be this one here. That is material A, and it's cesium chloride solution. And that's all we have to do. Got a bar in the graph to show the expected swelling for material A in a salt solution of strontium chloride. Right, I had a little puzzle with this one. I think maybe what they're wanting is if you look at the group 1 elements, as you go down group 1, the values are increasing. If this is then the group 2 elements, you can check that in your data booklet if you need to. Here, this would mean that we would be increasing as we go along. So anywhere between the calcium's number and the barium's number, that should be enough to pick up the mark. Maybe we wanted to figure out what they wanted. I go maybe somewhere like there, and then run that down. So my one, that would give us about 25, 26. So that should be okay. Here, they are measuring the time taken for absorption of 100 centimeters cubed of water. If a beaker is used, beakers are not particularly good at measuring. They're not very accurate piece of equipment. A measuring cylinder would be a more appropriate one. You could say burettes and pipettes. That's when you want very accurate readings. In this sort of experiment, we're comparing the time it takes for absorption. A measuring cylinder is more than acceptable. Next up, we want a graph. And this one is not going to be a bar graph. We're going to plot our points and we're going to draw our curve or our straight line. The thing that you are changing is the mass of the material between the experiments. So that means that has to go on the bottom. That is in grams. And then on the y-axis, going up and down the way, I would just copy what is written in the table. That way you know you've got the right label. That is in seconds. So along the bottom, our biggest number is going to be 1.0. We go up every 2 big boxes is 0.2. Next up, we've got 5 big boxes. So I'm saying this is a big box to play with. We need to get up to at least 180. If we go up in 50s, 50, 100, 150, 200, 250. This would work. The biggest number would be just about here. That would be acceptable because it's taking up half the graph. Maybe 40s though might be a little bit nicer. As long as you take up half the graph paper, you'll be fine. Some values are easier to calculate where your number sits on the line. We'll see what happens here. So first one, we have no value for 0 mass. We do not put any point at 0. Our first answer is at 0.1. Let me zoom out, make life a bit easier. So at 0.1 grams, that will be halfway between the 0 and the 0.2. So here, you could write them all in if you want. So 0.1, 0.2, 0.3, etc. Right, put in the rest of the values as well, just to make life a little bit easier. Okay, so there is no value at 0 grams, so we don't need a point. At 0.1 grams, we go up to 180, which would be here. At 0.2, we're at 160, which would be here. At 0.5, we would be up at 90. Now, there's not a 90 written on my graph, but 90 is halfway between 100 and 180. So it'll be 2.5 boxes up. So right in the middle, right between the two of them. Next, what we could do is we're looking at 0.7, which is over here. And that needs to go to 50. Similar to the last one, 50 is halfway between 60 and 40. So that looks good to me. And then at 1, we're at 30, which is halfway between our 40 and our 20. Now, if you're unsure of what each little box would be, one thing that you can do is, well, between 0 and 20, there are 5 little boxes. So 20 divided by 5 gives you 4. So each little box is going to be 4. To check it, you can say, well, it's 0. That would be 4, 8, 12, 16, 20. That works. So looking at the last one we did, which was up at 30, this was 20. This would be 24. You would then have 28. If one box is 4, half a box would be 2, and that gets you up to the 30. That's how you could do it. I just prefer to do it halfway between. That works for me. Makes sense to me. But you could divide the number of boxes by the gap that it's spreading across, and that'll tell you what each little box would be, and use that to get your answer. This is looking a bit like a curve, so I would probably do some sort of curve. You do not want to start your curve the very left hand side, because we do not have a value for that. We want to try and have a smooth curve that goes through the different points. Something along the lines of that. So something like that, but maybe a little bit smoother. Get 1 mark if you do a graph that has the points rather than the bars. Get 1 mark if you have suitable scales. 1 mark for the labels and units on each axis, and 1 mark for all the points plotted correctly, and a nice smooth curve or straight line. Even if my curve wasn't particularly good, I might lose that mark. I'd hopefully have picked up at least the other 3 for the right type, the scale, and the labels and units. Moving on to question 7. We have to name the 3rd member of the silane family. Silanes are not going to be a chemical you have covered in your course, but we have got the naming convention, which goes mono, di, something, tetra. That would have to then be tri, mono, di, tri, tetra, penta, hexa. It would be a tri, silane. Next up, calculate the number of hydrogens in a molecule of pentansilane. Easiest thing to do is just follow the pattern. As the number of silicons goes up by 1, the number of hydrogens goes up by 2. This would suggest that there are going to be 12 hydrogens in that molecule. Next, we have to predict a boiling point as we are making our way down the silanes. I'd be looking to see how much has it jumped by in each of the previous steps. This point has been up by 97. Then it's gone up by 68. Then 55. Gap is getting smaller every time. That's now 44. What this would suggest, this will be something that's less than 44. I'd probably say it'd be something like 33, 32, whatever it might be. This means that if we do 153 plus that number that I've decided is 33, we'd get an answer of 186 degrees Celsius. The gap might have been even smaller. Typically going to be some sort of range. So a little bit below and a little bit above, but that's what I would aim for there. Only time there'd be one set answer is if the jumps were exactly the same each time. There was a direct pattern between them. And here all we can really say is it's getting smaller. So that should be okay. Next up, we have to draw a diagram showing all the outer electrons for monosilane, SiH. First thing, how many electrons does silicon have in its outer shell? That is 4. They would be arranged around the points of a compass. We have hydrogen. Hydrogen is number 1. That's only got 1. Now, hopefully what we can kind of picture is that, well, if you've got your silicon here, we could join on our 4 hydrogens around like so. And then what we would need to make sure to make clear is that those 4 electrons from the silicon are still there. But we now have each hydrogen has brought along its own electron. And now, silicon now has an outer shell of 8, which makes it stable. Each hydrogen has 2, which makes that stable. That would be your diagram with outer electrons. There are other diagrams you can draw. You could draw dots and crosses instead of all crosses. You could draw petals. This is my preferred one. I think this is the easiest one, so that's why I'm going to do that. Why would something have a higher boiling point? This is to do with the intermolecular forces. Intermolecular forces are the attractions between molecules. So pent is bigger. And as a result, it will have stronger intermolecular forces for that. This question is one of our calculation questions. We have to calculate the mass of disilane. That's what I need to do at the end. That would be produced from 6 grams of silicon dioxide. So we have been told the mass is 6. That means we can use mass, GFM, and number of moles. Silicon dioxide is this chemical here. Disilane is over there. Now, the key to this one is there is a big 2, a balancing number of 2 in front of silicon dioxide. But for the GFM, I would recommend working off of the formula they have given us. What it's just telling us is that we have 1 silicon and we have 2 oxygens. Now, I know off the top of my head, the GFM of oxygen is 16, so it's 2 times 16. This one, I don't know off the top of my head for silicon. It'd be here though. Silicon, right there, 28. I'll give you 32 for that. Add them together gives you a GFM of 60. Going to free up some space. Up at the top of the page, it tells us that the number of moles equals the mass times the... It tells us the number of moles equals the mass divided by the GFM. N will equal 60. Will equal 6 divided by 60, which is 0.1 moles. Next, I would look at the ratio, comparing the two of them like in a recipe. For silicon dioxide to Si2H6, it is a 2:1 ratio. 2 there, nothing in front of the disilane, that means it's 1. So if we had 0.1 moles of silicon dioxide, we would have half of that, 0.05. This means I know the number of moles of disilane. I want the mass. I can figure out the GFM. We've got 2 silicons, which is 2 times 28. We have got 6 hydrogens. Hydrogen, again, is 1. In that data booklet. This would give you 56 plus 6, which will be 62. And to get our final answer, if N equals M over GFM, then M will equal N times GFM. That gives us 0.05 times 62, 3.1 grams as the final answer. Next question, you need to read the passage and then answer the questions. So once you've gone through it, next, name the compound found in some rocks from which phosphoric acid can be produced. I'm looking for phosphoric acid produced. I spot it here. So it's the fluorapatite. Next up, write the molecular formula for the chemical used to purify phosphoric acid. Find the word purify. Okay, I didn't spot that first. It tells you up here. It is purified using this chemical here. We need to just count up the number of carbons and hydrogens and oxygens. There are 1, 2, 3, 4, 5, 6 carbons. So C6. There are 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. And we have just got the 1 oxygen. So C6H12O would be the correct answer there. Watch when you're counting, sometimes it was very, very easy to count the same hydrogen or the same carbon twice. Do it a couple of times, just make sure you don't double count. We have got C6H12 for our answer. Next up, these chemicals contain phosphorus, essential for healthy plant growth. Healthy plants require NPK, nitrogen, phosphorus, and potassium. We talked about this earlier in the using your knowledge of chemistry questions. Going to be nitrogen or potassium. ADP is this chemical here. Now, when we look at that chemical, it does not contain potassium. It contains nitrogen and phosphorus. So for this particular question, I'm going to get rid of that one. It's only nitrogen that is in that chemical, which is also needed for healthy plant growth. Next up, sodium phosphate contains phosphorus, so it's a good fertilizer. Another property, now, a fact that you might want to just remember is that it needs to have NPK and needs to be soluble in water. It needs to get up through the roots into the plant. Now, sodium phosphate is hopefully, we go to page 8 and look at sodium phosphate. It's here, it is very soluble. This means it can get up into the roots. So I got that just because I know that's why they're used as fertilizers. But data booklet would help us with that. In terms of the properties, we want percentage by mass. That relationship is in the data booklet. Percentage by mass is mass divided by the GFM times 100. First thing I would do is just work out the GFM. Got 3 times hydrogen, 1 times phosphorus, and 4 times oxygen. I know oxygen 16 and hydrogen's 1. Phosphorus, I think I know, but it is 31. Believe me or not, that is what I was going to say. So 4 times 16 is 64. Plus the 3 for the hydrogen and the 31 will give you 98. 98 goes on the bottom. The chemical we are asked to care about is phosphorus. That has a mass of 31 and there's only one of them. So it would be 31 over 98 times 100. That will give me 31.6% is phosphorus. If you were asked a different question to talk about percentage of oxygen, the GFM will still be 98. However, for oxygen, there's 4 of them, each having a mass of 16. You would do 64 divided by the GFM times by 100 to get your answer for that. So whatever mass of the chemical in question is in your GFM, you use that in your calculation. Next, we're asked to separate calcium sulfate from phosphoric acid. Up in the paragraph, it tells us that it is a solid produced along with a liquid. If you want to separate a solid from a liquid, filtration, filter paper, and a funnel will be your easiest way of separating them. Filtration. State the number of moles of water present for every 1 mole of calcium sulfate in the hemihydrate form. All sorts of big words at me today. Hemihydrate. Oh, if we look here, there are half a mole of water. The dihydrate, it says, has 2. So that would work out. Yeah, that's what it is. So hemi means half. So 0.5 moles water. Make sure we're referring back up to the paragraph, the passage, to answer the questions. Most of them are directly from there, and that picks up your marks there. Next up, we are burning food, and we're asked to calculate energy. We are using a different relationship. We are going to use EH equals Cm delta T. Okay, so in this relationship, EH is the heat energy, C is the specific heat capacity of the chemical being heated, M is the mass of the chemical being heated, and delta T is the change in temperature. So we want to work out EH. C, for water, it is 4.18. It tells you in the data booklet. It tells you it's 4.18 kilojoules per kilogram per degree Celsius. So I can just pop in 4.18. Next up, the mass is the mass of the water being heated, not the mass of the food or the fuel. There's 10 grams of water. We need to put it into kilograms by dividing by 1,000. That's how our calculation works. That will be 0.01 times the change in temperature. Well, it started at 19, went up to 34. That's gone up by 15. And our EH will equal 0.627 kilojoules. Next up, we have got less energy has been absorbed than expected. The easiest one to talk about there is that heat was lost to the surroundings. Anyone who did the energy from fuels as an assignment will be very aware of that statement. We've also got a glass test tube. Glass is a worse conductor of heat than something like copper or some sort of metal. So that could be an alternative one. Another thing you could put as well is that if there's not enough oxygen getting to the food, it wouldn't burn fully. So you might have ended up with incomplete combustion. If you were doing this experiment in class, you might have found that the bottom of the can that you were heating the water in is covered in soot. That's because there's not enough oxygen getting to your fuel, and we're having incomplete combustion. This one is a proportion question. They're throwing lots of numbers at us, and we have to try and work it out as best we can. So first up, I tend to start at the end. It says there's a 30-gram biscuit. That would link to the fact that 1 gram of biscuit releases 20.9 kilojoules. So if we've got 30 grams, that's going to give you more energy out of it. So whatever number we get here has to be bigger than 20.9. How do I go from 1 up to 30? I can times by 30. I do the same on the other side. 20.9 times 30 give me 627 kilojoules. Next, it tells us that 1 kilocalorie is 4.18 kilojoules. We have 627 kilojoules. Now, I need to figure out a way of getting from 4.18 up to 627. Now, the easiest approach I've found is that if we can get our first number down to 1, and then from 1 you can go quite easily up to the 627. If you take any number and divide it by itself, that will give you 1. If you are starting at 1 and you multiply it by any number, you'll get to that number. So if I divide by 4.18 and then times by 627, that is the correct scaling process. We want to do those two calculations to 1. So we're starting with 1 on the left. If that started as a billion, start with a billion. So we take the 1, divide by 4.18, times by 627. That gives me 150 kilocalories. Cesium is highly reactive. Suggest a method to extract that from its ore. There are 3 methods for extraction. We have electrolysis for the reactive chemicals. We have heat with carbon or carbon monoxide. And we have heat alone. Best for most reactive, and then best for least reactive. They are straight up telling us that our chemical is highly reactive, so electrolysis would be the best approach. It states here that cesium ions are changed to cesium atoms. We go to the data booklet to the electrochemical series. Cesium is not on this, but we can use any of the other metals in its place. We are going from ions to atoms from the aqueous solution into a solid. To do that, we gain electrons. We can look at the top. They are describing the same change as all of these have. Therefore, our reaction has to be a reduction. This question wants us to talk about a beta particle. One of the earlier questions we had written that it's 0, -1 E. If it was alpha, that's the 4 to HE. Next up, we're talking about the thickness of materials the particles have to pass through. Alpha particles are easily stopped by paper, therefore will not travel through the material. That one. Next up, state what is meant by the half-life. It's the time taken for the radioactivity to half. You could talk about time for half the nuclei to decay. Next one, we're dealing with half-lives. So this one we want to calculate the fraction of the cesium that will have decayed after 120 years. Now, at the very beginning, we would have all of our cesium. After one half-life, which is 30 years, we would drop to having a half of the substance. If the question was talking about percentages, we'd do the same thing, but we would be talking about percentages. So going from 100% down to 50%. If they told you there was a certain number of grams of the material, so it might have been, say, 24 grams. Again, it's the same idea, but we're working in our grams, the material, the mass of that. In all situations, the value would drop by a half. Now, back to our actual question. We are told that one half life equaled 30 years. And they're asking us about 120 years. 4 half lives. 4 times 30 gives you 120. What this means is we need to do the halving 4 times. So after one half-life, it would be a half, then a quarter, then 1/8, and then the 4th halving would bring it down to 1/16, and it's 1/16 that's left. Question crucially says, how much would have decayed? We started at 1, we're left with 1/16. 15 over 16 has decayed. So the question crucially here says how much has gone away, how much is broken down, not how much is left. This question is asking us about tungsten fluoride. Previously, we talked about that if it's a metal and a non-metal, it would likely be ionic. However, you need to look at the rest of the information. So because it tells us that it is a colourless gas at room temperature, this must mean it's got low melting and boiling point. If it has low melting points and boiling points, it cannot be ionic. It's an compound, therefore it cannot be metallic. It has to be covalent. So this is whenever I'm describing or explaining bonding, I always say that metals and non-metals tend to be ionic, or usually ionic, not always. And this is important here. But it has to be covalent. Not going to be a lattice, because lattice is the word that goes with ionic and metallic. It has low melting points and boiling points. Therefore, it's going to be covalent molecular structure. If it only said the name, if the question didn't have this information here, then ionic lattice would likely be the answer you would pick. If there are properties, you need to deal with them, and that will get you your mark there. Next up, we're asked to balance this equation. The way I do the balancing is I take each element in turn and see, are they the same on both sides? If not, then fix it. W, we have got 1 and 1. That's fine. We have got 6 fluorines. We've only got 1 fluorine there. So I need to put a 6 in front of the HF. I always leave the hydrogens and oxygens till the end. The fluorines are fine. The W's, the tungstens are fine. Let's look at the hydrogens. Here I have got 6 hydrogens because I've got 6 HFs. So that's how I'm getting my count. There's 6 of them. Each of them had 1 hydrogen. That means then that we would need to put a 3 in front of the water to now give us 6 hydrogen as well. The auctions, we've now got 3 auctions. Each water has 1. We've got 3 of them. And we've already got 3 over on the other side. So that would be our correct answer. If you find it getting away from yourself, you can still get the mark if you've got, say, double the numbers. So if you had 2, 6, 2, and 12, that would work as well. If you're finding you have to keep changing numbers because nothing's making sense, maybe roll it back, start from the beginning again, and watch your counting. So making sure that you know that this means there's 6 hydrogens and 6 fluorines. And that might help you there. Describe the relationship of hydrogen ions and hydroxide ions in acid. If it's an acid, acids have more hydrogen ions than hydroxide ions. Next up, we have to complete the ion-electron equation for tungsten by adding electrons. We have got a 6+ charge here. We have got a 4+ charge there. There is a difference of 2. This means I'm going to want 2 electrons. Now, in terms of what side you want to put them on, if I was to put them on this right-hand side, well, now I've got 4 pluses and 2 negatives from the electrons. That would give me 2+ overall. They are not the same on both sides. That's not going to help us at all. If I put the 2 electrons on the left-hand side, I've now got 6 positive and 2 negatives. That will bring the charge down to 4 positive, and that means they are both the same charge on each side. It doesn't need to be 0, it just needs to be the same charge on both sides. Final question, second, using your knowledge of chemistry questions. We are asked to describe how a student can investigate a factor that affects the rate of chemical reactions. I would probably start with just writing down what are those factors. We have change in temperature, change in particle size, change in concentration, adding a catalyst. Now we have got hydrochloric acid reacting with calcium carbonate. From what we've talked about today, that's an acid plus a base. That will make a salt, particularly calcium chloride. Plus, we're going to get water. And because it's a carbonate, we're going to get carbon dioxide. Now, there's a gas being produced. Now, there's 2 ways we could do this. If we wanted to measure the mass of the gas escaping, we would use the one on the left with a balance. If we wanted to measure the volume of gas that's produced, we would use one of the 2 on the right. I'd probably draw the gas syringe one because it's just easier to draw. If we are going to say do temperature, so you could measure the volume of gas produced after 10 minutes. Repeat the experiment with different temperatures of acid. Calculate the average rate for each using the average rate equals change in quantity over change in time. And you can see the different values of them depending on that. If you want to do the mass one, you would just talk about measuring the mass rather than measuring the volume. Then do your change in mass over time. You're investigating the particle size, you used crushed and uncrushed calcium carbonate. Use different concentrations of acid. You could add, if there is one, a suitable catalyst and investigate other things we could say. We could tell them that this is a neutralization reaction between an acid and a base. Base is a chemical that neutralizes the acid, something like that. Something that can be kind of useful, we could put in. Could give an example calculation of gas produced in 10 minutes, then the rate would be 50 over 10, which would give you 5 centimeters cubed per minute, or something like that. That's everything I can think of currently. Again, quite possibly missed a bunch of stuff. As long as our answer is good to be pickable 3. If it was reasonable, we would get 2. If it was limited, we'd get 1. And that brings us to the end of the paper. That's how I would approach each of those questions. Thanks for watching. Goodbye.